guys, welcome to the third lecture. So the question is, if your A is in Rn, right, A under bar, or what you say this, A bar under bar. So A under bar is basically the pre-image. If you think this is a function, like let me go, which is very useful, you can say Rn to R a function. So we have this function, let's say x underscore this, let's say, as with the notation given in the question, a under bar is this, so x under bar goes to this sum. You can say that's a j from 1 to n, aj xj squared. So this is our function, right? So this function is what this function is. You can say this function is a polynomial function. So it's clearly what, for every a, you can say this is f of a, let's say under bar, this is better. So this is always continuous function, right, for all a bar belonging to Rn. So this is always a continuous function. So as a is basically the if a bar pre-image of this singleton one, as you can see, right, because we are finding those x's for which this is equal to 1, that is the pre-image, right? Yeah, so this is closed. So SA is closed subset of what? Rn, right? Yeah, so this is closed. Now we need to find the f for which SA is compact. Now in we know the compact subsets of Rn if and only if closed and bounded. So we are closed always, so we need bounded. So whenever SA is bounded, for which a bar we are collecting this a bar, so we are claiming that a bars are all, I mean, you can say this is the upper half plane, you can say all components are positive. This is our claim. Let's prove for which the what. Okay. So what we are doing here is our essay is closed, right? A subset of Rn. We need the boundedness, right? So we need the boundedness. Now let's claim a bar and a such that aj greater than 0 for all j 1 to n, right? This is our claim, for which we claim for SA is bounded, and that gives you the compactness, right? But why? Look, this is very simple, because we are giving so what is our SA? Formally, SA is in general this set inverse image of 1, that means this set that is 1, right? Now if each aj is positive, then your xij, which is also positive, and the sum is 1, so can it be unbounded? Never, because if one of the term is greater than 1, let's say xj square is greater than 1, what that means, let's say for example 2, right? Then I mean maybe yeah, then what that means, or let's say 2 by aj, then what that means, summation j from 1 to n, let's give it to k, and k not equal to j, then aj xj squared is equal to, or maybe you can say 2, okay, 2, this would be what, -1, contradiction, because why this should be contradiction, because some of the other terms cannot be positive terms, they all are positive, they cannot be added up to -1, never. So xj cannot be that much big to give this term either, right? So for a fixed a bar, you have a bounded term. Obviously if you make the each term smaller, then this can be bigger, but for fixed ages xj's are obviously fixed. In mathematically we can derive directly, so in a way we can show our aj xj squared together should be less than or equal to 1 for all j from 1 to n, right? Because any one of them cannot be greater than 1. If it is greater than 1, then things would be negative. Got it? Yeah. So that means our xj square should be less than or equal to 1 by j, and that gives you 1 by root of aj. As aj is positive, this is fine. So you simply get n-dimensional parallelogram, kind of parallelepiped, whatever, whose each jth side is less than or equal to this. I mean each jth side is this, so inside we are here, right? Some kind of n-dimensional, obviously it is 3-dimensional, but each side, this would be 1 by root a1, this would be 1 by root a2, and this side we have 1 by root a3. This kind of in 3D version, this is in 3D, of course, right? So obviously this is bounded, this is easy, but I just clarify. Now this does our claim, if it is positive then never. So for each, and now I can think of it that if your A2's AIs are very nearly to 0, then sites can be bigger, but for each AJ we can tend to 0, but we can have always a positive as we have claimed. So for each fixed one we have bounded, right? We always have bounded for each fixed one. Here we are not taking any limit. Each time we are taking a fixed one, and that will be obviously bounded. Okay. But if any of the AI is 0, what that happens? For that point, your xi can be any real number, right? Because that doesn't contribute to the sum. So suppose this is 0, so for which you can arbitrarily take it larger. So your SA bar is never bounded, is not bounded, right? And very importantly, and again, for if any of this is negative, the same thing will happen, because one of them is negative, one of them will be positive, and we can take xj such that they will cancel out. So they can be any bigger number and they can cancel out together. So xi and xj can be any real number. By twigging we can cancel them out, right? Yeah, do the same thing. Or all cannot be negative because the sum should be positive 1. So these two things will cancel out and giving you only this claim. So our FA. So what is our F? Rn such that A i's are positive. This is what our F is. So that you can say upper half plane. Now many people can think of it, why is the set? Because you take any of the point from the set, you get SA is bounded, because at a time you will take any point, right? Yeah, that is the set. And if we take any point in the complement of the set, so we see SA is not bounded. So if SA under bar should be bounded, then every A under bar should be inside the F, right? Because anything outside giving rise to unboundedness of SA bar, right? So that's it. There may be many people can think confusion, because points inside F, you can think whenever there are the many points now, there are points also very close to the 0, each component tending to 0. These points are also, but each time we are taking a point, we are not streaming, right? This is important, because this is each time whenever we pick up a point, we fixed it, we cannot tend to 0. However we close to 0, but this is not 0, right? So whenever this is not 0, so however the F touches the 0 line in each coordinate, right? But it never touches, it tends to touch, but it never touches. So this is the subtle change. Okay, this is the subtle thing that differentiate between our consistent world and the probabilistic world, you can say. This is something like a stream of flow of particles. If you are interested in quantum, in the double dual slit experiment, the electron particles flows. Whenever you detect one, it collapses and becomes a particle. Otherwise it becomes a flow of waves. flow of particles is waves. So you cannot detect any one. It seems that it is not particle. So similarly, if the set seems like it is a flow of points touching to the boundaries, but actually not. Whenever you observe any point or observe the flow inside the set, it gets collapsed to a single point, and which is completely, by the definition, never touches the axis. So yeah, for that point this is bounded, right? And again, if it touch the boundaries, SA bar would not be bounded. So that's why in the complement your SA underbar is unbounded, so not compact. So whenever compact, this is the F. So thanks for watching.